Overview of Key Specifications. Chapter 3. Every robot is designed for a purpose. From the way it moves to the tools and sensors it carries, each platform is built with specific environments and challenges in mind. Choosing the right robot isn't just a technical decision. It directly impacts performance, safety, and mission success. In the following sections, we'll explore the most common types of robots and where each one excels. When selecting or designing a robot, understanding its specifications is essential. These specifications define what the robot can do, where it can operate, and how it will perform under real-world conditions. To understand a robot's capabilities, we look at 6 key areas. First, mobility and locomotion cover how fast it moves, how far it travels, and how well it handles different terrain. Payload and manipulation focus on how much it can carry, how its arm moves, and what tools it uses to interact with the world. Power and energy include battery life, power usage, and how the robot charges, whether by plug, dock, or swappable batteries. Sensors and perception involve the cameras, LiDAR, GPS, and other tools the robot uses to see and understand its environment. Control and autonomy define how the robot is operated, manually, semi-autonomously, or fully autonomous, and how much onboard intelligence it has. Environmental resistance tells us how well the robot handles heat, cold, water, dust, shock, and vibration. These categories help evaluate what a robot can do and where it can go. A robot's ability to move effectively through its environment determines whether it can complete a mission safely and efficiently. Let's break down the key mobility and locomotion specifications you'll encounter. Speed. Max linear and angular velocity. How fast the robot moves and turns, usually measured on flat terrain, affects task time and maneuverability. Range. Range refers to the total distance a robot can travel on a single battery charge or fuel load. This is influenced by battery size, terrain, and payload. For autonomous missions like perimeter security or remote inspection, extended range is vital. Always consider both maximum range and effective operational range under load. Tracked robots offer superior traction and stability on loose, rugged, or inclined terrain. Legged robots, such as quadrupeds, excel in environments with stairs, rubble, or irregular surfaces. Look for specs such as ground clearance, maximum incline, measured in degrees or percent slope, and obstacle height clearance to understand what environments a robot can realistically handle. Maneuverability includes turning radius, agility, and the ability to navigate tight spaces. Certain platforms also feature multimodal movement, combining wheels and legs, or adding flight capabilities for hybrid drones. These systems offer extreme versatility, but may involve trade-offs in complexity, cost, and maintenance. In robotics, payload and manipulation capacity refer to how much a robot can carry, move, or interact with physically. These specifications are crucial for tasks involving lifting, transporting, or manipulating objects. Let's start with payload. Payload is the maximum weight a robot can carry, either on its chassis or with its robotic arm. This is typically measured in kilograms or pounds. It includes any tools, sensors, or cargo the robot must move. Exceeding the payload limit can reduce stability, increase power consumption, and even cause mechanical failure. Next, degrees of freedom, DOF, describe how many independent movements a robot or its arm can make. A simple 3-DOF arm moves up/down, left/right, and forward/backward. Advanced arms with 6 DOF add rotation and tilt for finer precision. For mobile robots, a differential drive moves forward/backward and turns, about 2 to 3 DOF, but can't move sideways. Mecanum-wheeled robots add DOF, enabling movement in any direction, including sideways and diagonal. More DOF means greater flexibility and accuracy for tasks like sorting, inspection, or assembly. Now let's talk about end effectors. End effectors are the tools at a robot's arm tip: grippers, suction cups, welders, drills, or multi-fingered hands, chosen to match the task. A robot's performance is only as reliable as its power source. Power and energy management are critical factors that directly affect how long a robot can operate, how far it can travel, and how demanding its tasks can be. First, battery life. Battery life is the time a robot runs on one charge, varying by size, payload, sensors, and activity. Small indoor units may last 1 to 4 hours, while larger mission-critical robots, like quadrupeds or drones, can be limited to minutes under heavy load or tough terrain. Second, power consumption. Power consumption, measured in watts, shows how much energy a robot uses. Motors, sensors, computers, and comms all draw power, so knowing average and peak usage helps predict runtime. Efficient components and smart power management can extend operations. Third, charging methods. Recharging methods impact uptime. Plug-in charging is simple but causes downtime, while quick swappable batteries can be removed and replaced in seconds, without tools, complex procedures, or long system shutdowns. Wireless docks let autonomous robots recharge themselves, ideal for 24/7 operations. Tethered systems get continuous power via cable, removing charging needs but limiting mobility. Power monitoring can track usage and warn of low levels, critical in remote or hazardous missions. For a robot to operate autonomously, it must first be able to sense and understand the world around it. This is where the sensor suite comes in. The sensor suite is essentially the robot's perception system, its ability to see, hear, feel, and measure the environment. Let's start with types of sensors commonly found on robots. Cameras provide visual data for object recognition, tracking, and navigation. LiDAR, light detection and ranging, emits laser pulses to create high-resolution 3D maps, excellent for obstacle detection and mapping in real time. Ultrasonic sensors measure distances using sound waves. They're simple, affordable, and great for detecting nearby objects. Infrared sensors are used for proximity detection and thermal imaging. Real-time kinematic, or RTK, is a high-precision positioning technique. RTK lets robots know their position within a few centimeters, which is crucial for mapping, autonomous navigation, and repeatable path following. GPS gives outdoor robots location data, while IMUs, inertial measurement units, track movement, orientation, and tilt. Touch and force sensors allow the robot to feel pressure or contact, useful in manipulation and human-robot interaction. Each sensor has its strengths and weaknesses. That's why many robots use sensor fusion, combining data from multiple sources to get a clearer, more accurate picture of the environment. Next is sensing range, how far or how wide a sensor can see. A robot-mounted LiDAR may scan up to 100 meters in all directions, while automotive-grade LiDAR can reach distances over 200 meters. A short-range ultrasonic sensor typically detects objects within 5 meters. Stereo and depth cameras add 3D perception, making them especially useful for mapping and obstacle avoidance. Understanding sensing range is important when planning the robot's movement and tasks. For example, a robot doing long-distance navigation outdoors needs long-range LiDAR and GPS, while a robot in tight indoor spaces benefits more from short-range sensors and cameras. Finally, there's data processing, the robot's ability to interpret what its sensors detect. Raw data isn't enough. The robot needs to recognize shapes, identify obstacles, measure distances, and make decisions in real time. This is typically handled by onboard edge computing systems, which process data locally for faster response and greater autonomy. In contrast to cloud computing, which relies on external servers, edge computing minimizes latency and allows the robot to function even without a network connection. At the core of every robot is its control system, the part that determines how the robot moves, responds, and completes tasks. Control systems are essentially the robot's brain, combining hardware like microcontrollers and onboard computers with software that interprets data and issues commands. Let's break this down by levels of autonomy, which describe how much decision-making power the robot has. Manual control. At this level, a human operator directly controls the robot, often through a remote, joystick, or computer interface. This is common in high-risk or sensitive operations like bomb disposal or confined space inspections. Semi-autonomous. In this mode, the robot can perform some actions on its own, but still relies on human supervision or intervention. For example, a robot might follow a set path, avoid obstacles, or return to a base automatically, but the operator still handles complex decisions or gives high-level commands. Fully autonomous. Fully autonomous robots can sense, plan, and act without human input. They interpret sensor data, make decisions, adapt to changes in the environment, and complete missions independently. For instance, a fully autonomous ground robot could patrol an area, avoid obstacles, identify threats, and return for charging, all without operator involvement. This level requires advanced AI, sensor fusion, and robust fail-safes to operate safely in unpredictable environments. This is the most common setup in field robotics today, balancing safety with efficiency. It reduces human workload while maintaining control over critical tasks. Control systems also define how the robot interacts with users and the environment. Some systems include real-time feedback, error recovery protocols, or adaptive behavior to adjust actions based on current conditions. When choosing or designing a robot, understanding the environment it will operate in is critical. Not all robots are built for every condition, and the right environmental specs ensure reliability and safety. Start with temperature range. Most robots operate within -20 degrees Celsius to 50 degrees Celsius. Outside this, batteries may fail, electronics can malfunction, and components can freeze or overheat. Cold start or cooling systems may be needed. Then consider weather resistance. Outdoor robots face rain, dust, wind, and sun. Look for IP ratings to gauge protection. IP65. Dust-tight, resistant to water jets. IP67. Dust-proof, survives short-term immersion. Use visuals or IP icons to help convey this clearly. Waterproofing matters in wet or submerged environments, like farming, sewer inspection, or coastal missions. Ensure enclosures are sealed, corrosion-resistant, and built to the right waterproofing level. Finally, assess shock and vibration tolerance. Robots in rescue, construction, or transit must withstand impact and shaking. Specs like G-force or vibration frequency show how rugged the design is. In short, match the robot's build to its environment, whether that's a clean office, muddy field, or stormy coastline, to avoid failures and keep it mission ready.